Welcome to today's webinar on creep analysis using Marc. My name is Srinivas Reddy, and I'm the Product Marketing Manager of Marc. And if you have attended our previous webinars in this series, you may remember that we did talk about modeling elastic plastic materials and also hyperelastic or rubber materials in the previous sessions. So today we will look at another of commonly performed nonlinear analysis, namely the deformation of materials that undergo creep. So first, I'll provide a brief overview of the creep behavior in materials and when these studies are important. Next, I'll give you a summary of capabilities available in Marc, after which we will go through a demonstration of the model setup and analysis in Marc. And also finally, we will close with a brief summary followed by Q&A. So we can broadly classify material models into two groups, namely time-independent and time-dependent models. In a time-independent formulation, the response is independent of the rate at which the loads are applied, and the deformations and stresses remain constant when the loads are constant. On the other hand, time-dependent formulations are used to model when the material behavior changes with time, and it's also dependent on the rate at which the loads are applied. So in the first group, we have models like elasticity and hyperelastoplasticity and hyperelasticity as well. And in these formulations, there is no time factor involved. So it does not matter whether you apply the load at a slower pace or faster in a static problem. The model would still give the same response. The second group aims to model the material behavior that is rate dependent and time dependent. The behavior changes depending on how fast the load is applied, and even if the load is maintained at a constant level. Notice that I'm not classifying the actual physical materials into these groups, but rather it is the material models that are put into these two groups. The reason is the same material can behave in both the time-independent and time-dependent manner, depending on specific conditions like the temperature or other environmental conditions, and even the stresses or any other loads that are applied onto the part. For example, if you take glass, it would behave as a brittle elastic material showing time-independent response at low temperatures. But when you heat it to close to glass transition temperature, it would start flowing, exhibiting strong time-dependent behavior at these higher temperatures. So in this webinar, we'll focus on one of the most common types of time-dependent behavior, namely creep. Creep is time-dependent, inelastic behavior that can occur at any stress level, either below or above the yield stress of the material. So creep generally becomes an important factor of structural designs, especially at higher temperatures, which typically range from 30 to 40% of melting point for metals and any temperatures above that. For materials like plastics and even low melting point metals and alloys, this can fall right in the normal operating conditions and normal environmental conditions that some structures could face. And for example, when the outside temperatures reach about, let's say, 110 degrees Fahrenheit, or which is about 40 degrees Celsius, you can see how the asphalt on the roads can get softer, and you can see it can start to flow and deform much more easily. And although creep can occur at stresses below yield, it generally is accompanied by plasticity when the stresses are high enough. So you may need to incorporate both the creep and plasticity into your model simultaneously. And also note that creep is inelastic, so which means that there is no recovery of creep strain when the structure is unloaded. So on the right side, you see the two plots. So when you have constant stress applied, so it is the material is undergoing creep. So the although the load is not changing, the creep strain keeps increasing. And kind of reverse to that is when you apply a constant strain. So here the material is experiencing a relaxation. So the stress is getting relieved at a constant strain. And let us see why we need to understand creep and incorporate the creep analysis into the product designs. And obviously, this analysis may not be needed for every product that you're going to design, but it is very important to understand it when the product temperatures get in the range of about 30% of the melting point of the material, as I mentioned before. And because if the creep strains are high, it could lead to product underperformance, and if the deformations exceed the tolerances, it could definitely interfere with the adjacent components and can lead to product failure. For example, if you take the blades of a jet engine, if the blades expand enough to contact the housing or other components of the engine, it could lead to a catastrophic failure. And also heat exchangers is another example, which may experience constant high temperatures and could experience continuous creep strain accumulation throughout their life. And the other very common example is the nuclear plant components, which also experience very high temperatures, and they are prime candidates for the creep studies. And of course, if you're dealing with plastics, as I mentioned earlier, the creep can set in at much lower temperatures, and this could become very, very important, even if the product is operating under normal conditions. And there are, of course, other uses for creep, especially in manufacturing. So the natural creep behavior of materials at these higher temperatures is used in manufacturing processes like creep forming. And in this process, a sheet can be heated, and you can let it deform under a constant pressure, and sometimes even under its own weight to obtain a desired shape. So some examples where this process is used include some aircraft panels and also some shaping of some glass sheets. So it is very important to understand and optimize the process parameters to achieve the best results in the fastest time. So here you see a typical graph of accumulated creep strain, and it is shown as a function of time. And you can also see that it is broken into three different regions, which is called a primary, secondary, and tertiary. The strain in the primary region, typically it's about 1%, and you can see that strain rate decreases with time, and it reaches a near constant value, entering at that point into a secondary creep zone. So in the secondary creep zone, so the strain rate at this point is relatively constant, and so it is sometimes also called steady state creep. And in the final stage of tertiary creep, the strain rate can start to increase much more rapidly, and it can lead to necking and failure or creep rupture. This curve can also depend both on temperature and also the stress level that is experienced by the part. So here I do not show all the dependencies, but for higher stresses or higher temperatures, the curve can be, you may have to plot different curves. So there are multiple mechanisms of creep that can come into play depending on the specific material and the loads and temperatures experienced by the structure. And once again, I won't go into detail of these mechanisms here, but a couple of examples in dislocation creep. The creep is controlled by the movement of dislocations in the metals, and it is dependent on the applied stress and temperature, with stress having a more dominant effect. And in the case of diffusion creep, the atoms diffuse along the grain boundaries and then elongate those grains. And this mechanism generally exhibits very strong temperature dependency. So you see this mechanism generally at higher temperatures. And also the polymeric molecular structure is quite different, and so their behavior is very much different from the metals. And viscoelastic material formulations are generally used to model the time-dependent response of the polymers. But I won't be discussing that part, like where discuss the creep of the polymers in this webinar. And however, more details are available in the Marc documentation. The creep strain and the strain rate, as I mentioned earlier, they are generally dependent on stress, temperature, and time. So you would see the various formulations of the creep functions for the various materials. They're shown in terms of these variables. There are several models in literature and which are developed for specific classes of materials. Also, power law is probably the most commonly used one. So with that background, let us now talk about how we can provide the material parameters to Marc so that we can perform the analysis. Since there are several forms of creep law available for different classes of materials, it is not possible to cover all these models within an FEA solution. So the most commonly used one is the power law or Bailey-Norton law. And here, the creep strain rate is represented as a function of equivalent stress, the strain, and also temperature and time. You see the exponent terms on the equation shown here. So here the coefficient A is the material constant, and so are that M, N, P, and Q. They denote the amount of influence that the stress, strain, temperature, and time have on the creep strain rate. You may not necessarily have all these constants in your model, because if temperature is constant in your application, you can, for example, leave out the temperature. You may not need that term for your analysis. And here is the snapshot of the material data input screen in Marc GUI. And you can leave the exponents that you don't need to use. So for example, if you want to define a creep rate function, again as a power law, that depends only on the stress. So you would definitely need to have a non-zero value for the exponent, for the coefficient, and for the stress dependence exponent, you would have a non-zero value. And you can leave out the rest of them at 0. And if you want to add their dependencies, you can modify the equation, and you would add the exponents for the other terms as well. And let us now look at some of the other options in providing the material data to Marc. So instead of providing the coefficients, so you can also provide the inputs in the form of the tabular data. So if you do that, you should provide the creep strain rate as a function of each of the variables. And so, for example, if you have the data in XY format with y-axis showing the creep strain rate and x showing the stress, you can read in this data into Mentat and ask the solver to use this data. On the other hand, if you have the creep strain rate as a function of both stress and temperature, you can read that as well, except that you would now need to have multidimensional tables in a specific format that the Marc GUI requires. So if you format it in that manner, you can definitely read the information back into Mentat. But notice that when you have these tables in multiple dimensions, it can get a little bit tricky, though, to visualize the information. And if you have a curve fitting program, it might make things a bit simpler if you actually go ahead and perform the curve fitting operation. And if you have already curve fitted the data, you would have the coefficients that would characterize the material. And we saw one formulation before, which was the power law. But again, as I mentioned, that is not the only one out there. There are very different formulations available for creep, and you may want to use a different equation, which might be better suited for your material. And so to facilitate this, Marc provides another method of input, which also uses the tables, but instead of actually reading the tabular data, you can provide equation for this multidimensional function. So Marc would then use this function instead of the discretized data. You can define any type of function as long as it is continuous, which means there are no step functions or no discontinuities. And I will show these options during the demo in just a few minutes. So there is yet another method where you can define your creep with the help of user subroutines. And this probably gives you the maximum flexibility and most user control. And this is very useful when you're dealing with new or special materials. And I'll not be covering the user subroutines, as that can be a separate topic in itself, and also in reality not everyone needs to use them because of all these several options available within Marc. So at this point, I'm going to show a quick demo. So this is the problem we're going to look at. So here I'm going to use a simple example of a tube, and a constant pressure is applied on this inner surface. And there are two symmetry planes, so I'm actually showing only one half. And also there is another symmetry plane. I'm going to model this whole thing, the whole half section in this analysis. And in addition to that, again, there is a pressure, as I mentioned, and as of material properties, so these are the properties I'm going to use. So we have the modulus and Poisson's ratio. And the creep law is, you'll notice that this is a power law with the dependence only on the stress. The creep strain rate dependence is only on the stress. So it is linear dependency on time. So let me bring up my Mentat screen so that you can see the model. So here we have the model, and as I mentioned, we do have some boundary conditions. Let me show these boundary conditions here. I do have a symmetry boundary condition, which I already applied, and there's another symmetry that applied here, but I'm still modeling the entire half. And I do want to show this how to apply the other boundary condition, which is the pressure So that's why I did not yet add here. So let's say we're going to add an edge load, and we want to select all these edges that are inside. So first step is to make sure we have selected those edges. And let me go ahead and apply the pressure, specify the value of the pressure. So that's the value I'm using in this analysis. And so let's go to select. Let me move the screen. And I'm going to use what we call the edge flood to make it easier to select it. And let me zoom in so that I select the appropriate edge. So now it is at edge flood, and so I want to select all the edges interior. So I select an edge here, and you notice that we have 50 edges selected. And let me apply the pressure to those edges, and I want to apply everything that is selected. So you see that we have the pressure on all these interior edges. So what happened when we used the edge flood is, once we selected the edge, it went ahead and selected all the adjacent edges, and as long as the angle between those adjacent ones is less than 60 degrees. So here, once we hit this sharper corner, obviously the angle is higher than 60, so the selection did not go beyond that. So this one makes it much easier to actually select all these interior edges. So we have the boundary conditions selected, and let me also go to material properties, and I'm going to use define a new material. So we have this structural and the properties. First we specify the modulus. In this particular one, I'm not using any plasticity. So there's no plasticity in this one. If at all you do, so you can definitely go ahead and add your work hardening curve under plasticity in addition to the creep. So I go to creep, and we have the power law, and I enter the coefficient that I showed earlier. I think it's actually 4e minus 24, and this is 4.51, which is the stress exponent. So we have the material properties defined, and I apply the property to, once again, all the elements here. So we have the material defined, and so this is how you actually define your creep material properties. And the next steps are not very different, so they're very similar to the other analysis. Only thing I would say is when you define the load cases, you do need to remember that the time that you put, for example here, this one, unlike in a quasi-static analysis where the time represents more of how fast you want to load it, it's more of a dummy variable, but here the time has specific units. It could be a second or hours, and so you do need to pay attention to that particular aspect. So you need to specify the initial time step, and when you say maximum time step of 0, so we're not placing any limit on the maximum time step. Otherwise, you can limit the maximum time step as well. And you see the total amount of time that this analysis is run for. So essentially, that is all that we need to do, different for a creep analysis compared to other time-independent analysis. And before going to the results, though, I do want to show a couple of other options. As I mentioned earlier, in addition to defining the power law, we can also import the material properties or define the material properties using the tables. So let me go over there. And first thing, let me read in data, and actually let me not select the proper format, so using the raw data, and so we do have this table defined. So we have there, this is the curve. Actually, this is the same curve that I defined in using the power law. I just plotted a few points so that we get some discretized table. Let me get rid of this selection panel. We don't need that anymore. Then once that is done, we can go to materials and select the table. But before going there, so let me I just say PL for piecewise. So I just name it, and then we can also, let me define a new table. This is once again with table. I'm going to make this even the prior one. Yeah, we should make it dependent on the stress, because this function, this particular variable is equivalent stress, which is the independent variable. What we can do here is, instead of reading the data points, you can go to formula, and I can enter the actual formula for that equation. And V1 power 4.51. I'm using the same one, just same power law, and it could as well be anything else. It doesn't have to be the power law right here. So we reevaluate and go ahead and fit. So you see that, well, right now we chose 10 points, so that is why we have only 10 points. If we make more, and then we can reevaluate to more. But either way, it is not going to use these data points, but actually it is the function that is going to go into Marc. But sometimes it might be good to see the actual curve with more data points. So you can adjust the data points here for visual purpose, but it is the function that actually gets imported into Marc. So we have this, once you have the tables defined, so you can go into structural and creep, and instead of power law, we can say piecewise linear, and make sure we have ones, because that is a multiplying factor for this table. And you can select either the piecewise linear one, or we can use this. And once you do that, instead of the power law, we are actually using this other set of data. So that is how it's you can use the tables to model creep data that may not fit into the power law. So with that, let me quickly show the results for this analysis that we have done. And I'm opening the results. And let's say, go to contour bands, and once again, let's select a creep strain. And we can definitely monitor the results. There are more than 1,300 increments, so it will take a minute or so to get to the final one, so I'm not going to wait until then. So let's just quickly skip to the last increment. And so this is the final deformation of this tube. So another thing that is generally very important is to look at how it is progressing, right? So history plot is one common thing that is used for this creep analysis. So let me go ahead and show a plot so that we can see the time variation of creep strain at one location. So let's pick that node, and we say we want to look at all the increments. Basically, plot the data for every single increment. So it is almost done. It's about 1,300 increments. So we're done with that, and go ahead and add a curve. And again, I could say single location or all locations because there's only one anyway. So say time and the creep strain. So go ahead and fit. So you get to see. So with time, obviously in the very beginning, it has the creep strain does go up quite a bit, but then it is flattening out. So after a certain time, you don't see too much of an accumulation of creep strain. So this is what I have for the demonstration purpose itself. There are definitely a lot more options for creep analysis, and you can get the details of all that in our user manual, and there are a lot of examples as well. So with that, let me quickly summarize what we have covered in this presentation. So we talked about the importance of the creep and what creep is, and also its influence on the structural designs. And I also talked about the models that are available and how to provide inputs to Marc. And we also looked at a model and also how to set it up in Marc and how to run the analysis. And so note that you can definitely model and solve any type of complex time-dependent material behavior using Marc. And I hope this gives you an overview of what is possible. And you can definitely look through the documentation if you have access to it, or you can also contact anyone at MSC, either the account manager or any unit that you know, to get a more detailed understanding of the Marc's capabilities for this type of analysis. So that concludes the main part of my presentation.